Every single person listening right now has experienced it. That moment when you tap an app and it just hangs, or you start scrolling and the whole thing freezes, or worse, it crashes completely, sending you straight back to the home screen. That momentary feeling of frustration is what ultimately separates a truly world-class mobile application from one that, gets relegated to the dilution pile before the next major update.
It's absolutely true. In modern software development, the functional features, what the app does, that's really only half the battle.
Right.
The difference between an app that just sort of works and an app that excels often boils down entirely to mastering these non-functional requirements. Stability, speed, reliability.
Especially under pressure.
Exactly. This is especially true under the stressful conditions mobile devices constantly face, whether it's like poor network connectivity, throttling from the operating system, or maybe running low on memory. We're not just talking about coding features. We're talking about engineering software resilience, a different mindset.
And today, we have access to an incredible resource. We've managed to distill a massive set of highly detailed technical Q&As sourced from expert forums, deep architectural reviews, high-level developer debates, that kind of thing. This material gives us a direct masterclass outlining the precise investigation steps and proven solutions top developers use to conquer the most common, complex, and frankly, high-stakes mobile troubleshooting scenarios.
Yeah, like the really tricky ones.
We're talking about everything from those pernicious memory leaks and race conditions to fixing flaky push notifications, stuff that drives users crazy.
And our sources provide a pretty comprehensive blueprint for operational excellence in mobile development. It's essentially a shortcut past years of trial and error and, let's be honest, painful debugging sessions.
Oh, definitely.
Our mission today is to walk through the 5 core pillars of a robust mobile app, breaking down exactly what tools these experts deploy and what specific architectural patterns they prioritize to keep the user experience absolutely fluid and reliable.
That sounds like a technical investigation we can really sink our teeth into.
Yeah.
Okay, let's unpack this. We have to start where every user's worst nightmare begins. Application killers. Crashes and memory leaks. They're the immediate stability threats that just erode trust instantly.
Right away.
Let's look at a classic high-volume scenario that drives developers and users nuts. Random app crashes occurring frequently while scrolling a high-volume data view like a UItable view or UI collection view. What's the very first step in the investigation procedure here? Like, where do you even begin?
Well, the first and arguably most important step is replicating the issue consistently. You need to confirm the nature of the crash.
Okay.
Experts should immediately try to replicate the crash on older or lower spec devices, or maybe using low memory simulators.
Why specifically those?
Because if the crash is much easier to trigger under these constrained resource conditions, you've basically confirmed that the issue is resource related.
Ah, okay.
It's not just a random logic error or maybe an API fault. It's likely a structural deficiency in how the app handles memory or processing load. That's a huge clue.
So once we suspect that resources are the core culprit, what specialized tools are we deploying? Because a seemingly random crash in a scrolling view feels like finding a needle in a haystack.
Yeah, it does. You absolutely need deep observability into the system's memory allocation. You'd start by using the standard Xcode organizer or integrated third-party crash reporting tools like, say, Crashlytics or Sentry to get the initial stack traces.
But that just tells you where it died, right?
Exactly. Those only tell you where the app died, not why it ran out of gas, so to speak.
Yeah.
To pinpoint underlying high memory usage or specifically active memory leaks, you must deploy the instrument suite.
Okay, instruments.
We're looking for instruments, specifically the allocations and leaks profiles. This is really the only reliable way to confirm if memory is just climbing too high or if objects are failing to be deallocated when they should be.
Let's nail down the fix then for those volatile scrolling views. If the user interaction itself, the scrolling, is causing the crash, the optimization must be pretty ruthless, I imagine.
It must be, yeah. The sources highlight 3 crucial kind of non-negotiable optimization steps for table views and collection views. First, ensure you are reusing cells properly using the Dicker usable cell method.
That sounds basic, but I guess people forget.
Oh, definitely. If you fail to do this every time the user scrolls, the app will initialize hundreds of brand new view objects, which is just guaranteed to exhaust memory quickly. The whole system is designed for reuse. You have to use it.
That's pure object creation overhead.
Okay.
Okay, what about what's happening inside the cell itself?
That's the second critical step. You must strictly avoid any heavy computations, complex date formatting, or raw image processing right there within the cell setup method, self-farad.
Because that gets called constantly.
Constantly. This function fires dozens of times per second during a fast scroll. If the main thread is tied up doing heavy lifting here, the UI cannot update. That leads to dropped frames, stutter, and eventually, the crash.
And the third point, images.
Images. Third, you must ensure you load images asynchronously or lazily. Image loading has to happen off the main thread. You should only be fetching the images the user can currently see. Otherwise, the scrolling will simply lock up. It's a very common culprit.
That distinction between just performance optimization and actual stability is crucial there. Now let's move into this silent killer. Memory leaks caused by retain cycles. These are sneaky.
Very sneaky.
Explain the core problem and how developers detect these issues that don't immediately crash the app, but sort of slowly strangle it over time.
Yeah, the core problem, put simply, is objects creating strong circular references to each other. If object A holds a strong pointer to object B, and object B in turn holds a strong pointer back to object A, well, neither object's reference count will ever drop to 0.
So they just hang around forever.
Exactly. Since neither can be safely deallocated, they remain in memory indefinitely, just consuming resources until the operating system steps in and force quits the entire application due to high memory pressure.
Wow.
It's death by circular dependency, and it's insidious because the app might appear fine for a while until the system is really stressed.
So the memory allocated to those objects stays allocated forever. How do you find them? What's the tool?
Beyond the leaks instrument we mentioned, developers rely heavily on the Xcode Memory Graph Debugger.
Memory graph debugger.
Okay, yeah. This tool allows you to literally pause the app and visualize the relationship map of all live objects in memory. You can right-click an object you suspect should have been deallocated and see exactly which other objects are holding a strong reference to it. That circular link becomes immediately visible. Quite powerful.
Once identified, the fix often involves weak or unowned references, especially in closures. Can you differentiate clearly between those two options, weak self and unowned self? When do you use which?
Right, this is a vital architectural decision. When developers use weak self in a closure, they are basically accepting the possibility that the captured object, often self, the view controller, might be deallocated before the closure finishes executing.
Okay, so it could disappear mid-closure?
It could. And because of this possibility, self becomes an optional type, self, that requires conditional unwrapping or optional chaining. Self.do something. This is the safest approach and honestly should be the default, as it prevents crashes if the object just disappears unexpectedly.
Then owned.
However, unowned self is used when you are absolutely certain, like 100% certain, that the captured object will always outlive the closure's execution.
Always. That sounds risky.
It can be. It avoids the tiny overhead of optional checking, but here's the critical warning. If you're wrong, if the captured object is unexpectedly deallocated first, accessing it via an unknown reference will result in a catastrophic runtime crash. No warning, just boom. Yeah. The sources really emphasize, use weak unless you have a very specific high-performance reason and absolute certainty to use unowned. Generally, just stick with weak.
And we also see this pattern with delegates. Why must delegate variables always be declared as weak? Is it the same principle?
Pretty much, because the delegate pattern inherently creates an inverse relationship. The delegator, say a table view, needs a reference to its data source or delegate. But the delegate, often the view controller, is usually the one that owns or holds the table view in the first place.
Ah, so A holds B and B holds A back.
Exactly. If the view controller A holds the table view B and B holds the view controller A as its delegate strongly, you have an instant retain cycle. Declaring the delegate variable as weak is the fundamental systemic pattern to break this specific cycle. It's really a non-negotiable rule in high-quality iOS architecture. You just always do it.
Before we move into performance, let's focus on one specific crash that always signals deep, low-level trouble. XXE beta access. It's notorious for being hard to trace. What does that crash fundamentally signify?
XE beta access.
Go!
Yeah. That crash is essentially the system yelling at you, you tried to touch memory that is no longer yours. It means you are accessing an object that has already been deallocated, a classic dangling pointer scenario. Since the memory address might have been reused or freed, the app crashes unpredictably when you try to access that old, invalid location.
And the specific tool for this is what you call the zombies feature. Can you elaborate on how that actually works? It sounds dramatic.
It sounds dramatic, yeah, but the mechanism is invaluable. When you enable zombies in Xcode's scheme diagnostics, the system handles deallocated objects differently. Instead of immediately freeing the memory when an object's reference count hits 0,
It keeps it around.
sort of, the object is replaced with a special placeholder zombie object. This ghost object sticks around just long enough to detect if something illegally tries to access it later.
Like a trap.
Exactly. The key benefit is this. When the illegal access occurs, instead of just crashing at some meaningless memory address, the zombie object intercepts the access and reports precisely who tried to access it, when they did it, and what object they were trying to reach.
That's incredibly useful.
It is. This logging allows the debugger to catch the exact moment the illegal access occurs and trace the pointer back to the originating unsafe line of code, something nearly impossible to figure out without the zombie tool enabled.
Okay, so we've stabilized the app, hopefully eliminated the random structural crashes. Now we pivot to performance, which is all about perception, isn't it?
Very much so.
If the app feels slow or stutters, users assume it's broken, even if it hasn't technically crashed. Let's tackle the dreaded slow app launch, an 8-second launch time. That's absolutely unacceptable in mobile time.
It is, yeah. If your app launch is that long, your user attrition rate is going to be terrible. Users just lose patience very, very quickly.
So what's the approach?
The first step, just like with crashes, is rigorous measurement. You have to know where the time is going. You must use instruments, specifically the time profiler, or maybe the more modern signpost framework, to precisely locate where those seconds are being consumed.
Like finding the bottleneck.
Exactly.
Yeah.
The time profiler shows you the execution path of the app. You could literally see if, say, 70% of your launch time is spent initializing a database or making a slow synchronous network call right at the start.
And the foundational principle that keeps coming up across all our sources, across pretty much every performance question, is main thread protection. Why is this the holy grail?
Main thread protection is the mantra because the main thread is solely responsible for handling UI updates, touch events, animations, drawing, basically everything the user sees and interacts with.
It's the UI thread.
It's the UI thread. If the main thread gets blocked for more than about 16 milliseconds, that's roughly one frame at 60 frames per second, the user experiences dropped frames and the app visibly stutters or just freezes. Therefore, any heavy, time-consuming work network calls, extensive database queries, complex JSON serialization, parsing large amounts of data, it must be immediately moved off the main thread and run asynchronously on a background queue. No exceptions.
Beyond just moving heavy work off the main thread, what other specific architectural optimizations are recommended for lightning-fast launch times?
Well, it's really all about deferred initialization and lazy loading. First, try to reduce the depth of your view hierarchies. Flatter view structures just render faster.
Simpler is better.
Simpler is faster. Use lightweight views, and if possible, leverage newer frameworks like SwiftUI, which are often designed for faster layout rendering. Second, cache. Frequently used foundational data things like user settings stored in user defaults or maybe core database schema information to avoid redundant network fetches or complex disk operations right at launch.
Makes sense.
But the golden rule is what we sometimes call just-in-time initialization.
Right.
Only preload absolutely essential resources required for the initial splash screen and the very first interactive view the user sees.
And delay everything else.
Delay everything else. Delay any non-critical initializations, like fetching advanced user analytics data or maybe pre-warming views for some deeply nested tab, until after the app is already visible and responsive to the user. Let them interact first.
Let's talk about images, because they seem like silent memory killers and a guaranteed source of stuttering if not handled right. High-resolution images cause memory warnings, crashes, especially in those scrolling views we talked about. How do experts manage this bloat efficiently?
Yeah, image management requires 3 sophisticated, coordinated strategies that really have to work together. First, caching. You absolutely must implement effective memory and disk caching.
Like using NSCache.
Using NXCache or reliable third-party libraries like SD WebImage or Kingfisher. This prevents the repeated and really expensive loading of the same image from the network or disk every single time a view scrolls back into site.
Okay, caching solves repeated loading. But what about the sheer physical size of the image data once it is in memory?
That's where the second step, downscaling, is absolutely vital. Developers must resize images to the exact display size before rendering them.
Before they hit the screen.
Exactly. If you download a massive, say, 50 megapixel photo just to show it as a tiny 100 by 100 pixel thumbnail, you are forcing the system to store and manipulate huge amounts of wasted data in memory. That's a guaranteed path to memory warnings and poor performance. You downscale it on a background queue to match the view frame it'll actually be displayed in.
Smart. And the third strategy, you mentioned proactive memory management.
Right, the lazy loading and, crucially, the releasing strategy. You load images only for visible cells. That's the lazy loading part. But you also have to proactively and explicitly release unused images when views disappear.
How do you do that?
The technical fix, as highlighted in the sources, is setting cell.imageview.image in enil when the viewer cell is prepared for reuse or scrolls off screen. This proactively tells the system, hey, that massive block of memory previously occupied by that image. You can free it up now. It helps keep the memory footprint low.
And if the image processing itself is heavy, say applying complex filters, maybe geometric transformations, or deep color adjustments,
then you absolutely move that intensive processing off the main thread. You'd use dedicated background mechanisms like dispatch queue.global or maybe an operation queue.
But can we do better?
We can go further, yeah. For true performance, especially for really heavy stuff, you should leverage GPU accelerated frameworks. Frameworks like Core Image or Metal are specifically optimized to execute parallel pixel manipulation tasks directly on the graphics processor.
Which is way faster.
Orders of magnitude faster and much more power efficient than trying to perform massive pixel manipulations solely on the CPU. Use the GPU when you can.
Okay, moving beyond static resources like images, let's focus on the actual fluidity of interaction. App stutters when scrolling or during complicated animations. That's a constant source of frustration for users. How do we ensure that butter-smooth scrolling experience?
Yeah, for traditional legacy UI elements like UI collection view, the stutters usually stem from calculations happening during the scroll itself. Things like layout calculations, frame computations, or maybe complex auto layout resolutions.
So do the work up front.
Exactly. The solutions involve offloading those calculations by pre-computing frames or layout attributes before the scroll even starts. You also need to keep the views themselves as lightweight as possible. Fewer layers, less complexity.
What about rasterization? I hear that mentioned sometimes.
Right, there's also the caution regarding should rasterize. Setting layer.should rasterize equal true caches complex layer content as a flat bitmap, which can speed up scrolling of complicated view hierarchies.
But there's a catch.
There's a catch. Developers must use it very sparingly. If used improperly, it can actually increase memory consumption dramatically. And if the layer content changes frequently, it forces continuous, expensive redraws of that cached bitmap, which kills performance.
So how do you know if it's helping or hurting?
You profile. You have to profile with instruments core animation. Look specifically for frame drops, and especially look for red-flagged instances of off-screen rendering, which rasterization can sometimes cause.
And for animations themselves, particularly those struggling on older devices, what's the fix there?
The main culprit there is often deep nesting of views. You simplify the view hierarchy, aggressively reduce the number of nested views, minimize off-screen layers that the system has to composite.
Keep it flat.
Keep it flat, and avoid continuous redraws by favoring efficient K-layer animations over repeatedly calling setNeedsDisplay on your views. Older devices simply don't have the processing headroom for unnecessary complexity or drawing loops.
Finally, modern apps often use SwiftUI, which introduces its own set of challenges, especially with rapid data updates causing flickering or stuttering animations. How is that managed using modern reactive tools like Combine?
Yeah, SwiftUI's reactivity is powerful, but it can be a double-edged sword. If data changes flood the system, say, you get 50 minor updates per second coming from a sensor or a fast network stream, the UI will thrash continuously trying to update.
Right, constantly redrawing.
Constantly. The solution is basically flood control. Developers use Combine's debounce or throttle operators to limit the rate of these rapid state changes.
How do they differ?
Throttle ensures updates happen at a maximum rate, like, say, once every 100 milliseconds, discarding intermediate updates. Debounce, on the other hand, waits until there's a short period of quiet, a pause in the updates, before committing the final state change. Both prevent the UI from churning unnecessarily.
What else helps with SwiftUI performance?
Also critical for SwiftUI performance is using stable IDs. You must use the identifiable protocol correctly in your list data structures so the framework can track items efficiently across updates.
Okay.
And when performing large bulk data updates, sometimes it helps to use the animation nil modifier to temporarily disable implicit animations. This can prevent visual flicker caused by views trying to animate rapidly between hundreds of intermediate states during the update.
All right, so when an app moves from just functional to truly robust, it has to handle data reliably, regardless of the network state, and manage shared resources safely without tripping over itself. Let's dive into offline support, which feels crucial for modern mobile experiences. People expect things to work even on the subway.
Absolutely. Designing for resilient offline sync involves not just storage, but really a multi-phased strategy. Phase 1 is local caching. You must use a robust structured storage solution like Core Data, Realm, or perhaps SwiftUI to store all the changes the user makes while they're offline.
Not just temporary files.
No, this needs to be reliable, probably relational storage, not just dumping stuff into temporary files that might get lost.
Okay, so you store the changes. What's phase 2? Tracking them.
Exactly. You need to queue operations. You can't just store the final state of the data. You need to track every specific CRU action vec. Create, read, update, delete that was performed while offline. This queue essentially acts as a transaction log, ready to be replayed when the connection comes back.
And phase 3 is the tricky part, I guess, the sync itself.
Phase 3 is the complex part, the sync logic. You use network monitoring frameworks, and maybe Apple's NW Monitor or an older reachability library to detect when the connection is restored.
And then replay the queue.
Once online, you must replay the queued operations against the server, usually in the correct order they happened. The hardest part, though, is resolving data conflicts.
What kind of conflicts?
Well, what if the user made local changes to an item, but while they were offline, the server also made changes to that same item? You have a conflict. You must use predefined server-side rules, or maybe timestamps, to determine which change wins or how to merge them. That logic can get complicated fast.
Speaking of conflicts, when core data stacks clash during synchronization, which I hear is common in multi-context architectures, how do you ensure data integrity without just blocking the whole UI while it sorts things out?
Right. This is where expert core data usage really shines. First, you need to select appropriate merge policies. Core data offers options like NS merge by property object trump, where the in-memory object's properties win, or NS merge by property store trump, where the persistent store's version wins. Or you might need to implement completely custom logic to intelligently resolve simultaneous updates based on your app's rules.
And how do you avoid blocking the UI?
Crucially, all the network updates, the parsing of the server response, and the heavy data processing that leads to the potential conflict must be performed on a private context or a background context.
Not the main one.
Definitely not the main one. This isolates the heavy lifting and the merging process from the main context, guaranteeing that the UI remains responsive and unblocked, even during potentially lengthy sync operations.
Now, for race conditions, you mentioned them earlier. They sound like the silent assassins of concurrency. For the listener, what exactly is a race condition, and why are they so difficult to debug?
Yeah, they are assassins. A race condition occurs when the outcome of your program depends on the unpredictable sequence or timing of different events, usually across multiple threads.
Can you give an example?
Sure. Imagine two separate background threads trying to read and then update the same shared bank account balance variable simultaneously. Thread A reads the balance, say $100. Almost instantly, thread B also reads the balance, also $100.
Okay.
Then thread A calculates a deposit of $10 and writes back $110. But thread B, which still thinks the balance is $100, calculates its deposit of $5 and writes back $105.
Oh, so thread A's deposit is lost.
Exactly. The final balance is wrong, $105 instead of $115, and totally unpredictable depending on which thread finished writing last. Because the timing is variable and depends on system load, these bugs are notoriously hard to reproduce consistently during testing. They might only show up under heavy load in production.
Nightmare. So how do high-performance experts ensure thread safety without just making everything run one at a time and losing all the concurrency benefits?
Right, you don't want to kill performance. The fixes are generally built around creating choke points and guarantees for accessing that shared resource. The simplest approach is using serial queues.
Like a single file line.
Exactly. A strict single file line approach. It ensures only one thread can modify the shared data at any given time. It's perfectly safe, but it can be slow if you have a lot of contention, a lot of threads wanting access.
What's the faster way?
The preferred high-performance strategy often uses dispatch queue barriers in conjunction with a concurrent queue. The beauty of a barrier is that it allows multiple threads to perform concurrent reading from the shared data, which is usually safe and happens most often.
Reads are okay together.
Reads are usually okay together. But when a write or mutation operation comes in, the barrier task essentially puts up a gate. It waits for all current reads to finish, then runs the write task exclusively, blocking any new reads or writes.
So writes get exclusive access.
Guaranteed exclusive write access for that single thread. Once the write is complete, the barrier releases the lock, and concurrent reads can resume. This gives you high throughput for reads while absolutely guaranteeing safety for writes. It's a really common and effective pattern.
And what role do modern Swift features like async await play in managing these complex asynchronous flows?
Well, async await and structured concurrency are real game changers here because they make the flow of control much more explicit and predictable compared to older callback-based or even some queue-based approaches.
How so?
Well, using features like Task Group, developers can manage multiple related asynchronous tasks within a defined, contained scope. This ensures, for instance, that all dependent network calls complete before the group finishes and you try to process the complete result.
And for things that need to happen in order.
For sequential tasks that absolutely must execute in a specific order, async await naturally dictates that sequence in the code, making it much easier to read and reason about than nested callbacks.
What about Combine?
Furthermore, tools like Combine, with its rich set of operators like merge, combine latest, or switch to latest, provide incredibly powerful ways to sequence, combine, filter, and control the flow of asynchronous event streams safely and declaratively. They help manage complexity.
Before leaving this data section, we need to clarify the fundamental choices for local storage. We have user defaults, core data, and just raw files. When do you pick which one? What's the rule of thumb?
It's purely about the nature and complexity of the data you need to store. If you need to store small, simple key value data like user interface settings, feature flags, maybe a simple authentication token, that sort of thing, user defaults is the easiest and most appropriate tool. It's built for that.
Okay, simple stuff. User defaults. What about more complex data?
If you have large structured data sets, data with complex relationships between different pieces like one-to-many or many-to-many relationships, or if you need sophisticated querying capabilities or robust persistence with features like under-roto, then core data is generally the best fit. It's designed for managing object graphs.
And files. When do you just use the file system?
Anything unstructured or large binary data. Think large cached images that don't fit well in memory cache, downloaded videos, or maybe just raw blobs of JSON or PLIS data that you simply want to dump to disk and read back later without much processing. For that kind of thing, using files directly is often the simplest approach.
Okay, that makes sense. And if you do choose core data, which sounds powerful but potentially complex, how do you prevent the inevitable performance degradation as the database grows over time? A big database can get slow.
Absolutely. Core data performance management is an ongoing task, not a one-time fix. First, you must avoid fetching the entire database or even large chunks of it all at once. Use fetch limits and, importantly, fetch batch size to retrieve data in manageable chunks, loading more only as needed, like when the user scrolls.
Okay, fetch in batches. What else?
Second, index frequently queried attributes. If a search takes way too long, it's often because the attribute you're searching on wasn't indexed in the data model, forcing core data to do a slow, full table scan. Indexing is crucial.
Good tip.
Third, ensure fetching is always done asynchronously using NS-asynchronous fetch request, especially for potentially large queries. This prevents the UI from freezing while core data does its work in the background.
Keep it off the main thread again.
Always. And finally, for certain lightweight operations where you don't need the full object data immediately, consider fetching only the NS-managed Objective-D references. These are much smaller and faster to retrieve than hydrating full NS-managed object instances in memory.
All right, a truly robust app needs to integrate seamlessly with the operating system, even when it's not the main thing the user is looking at. Let's start with the notoriously tricky subject of push notifications. Users reported they aren't receiving them reliably, or maybe they're severely delayed. Where do you even start the investigation for that? It feels like black magic sometimes.
It can feel that way. You really have to start by systematically checking the entire communication chain, right from the user's device all the way back to your server's payload configuration.
Okay, step by step.
First, on the device side, you absolutely have to confirm user permissions. Did the user actually grant permission for notifications? Use UN User Notification Center APIs to check that.
Easy mistake to make.
Very easy.
Yeah.
Then verify the entire APNS Apple Push Notification Service setup. Certificates, provisioning profiles, the app's bundle ID. They must match perfectly between your app build and what's configured in the Apple Developer Portal and on your server.
Lots of places for error there.
Tons. And crucially, ensure the device token That unique identifier for the device-app combo is correctly registered by the app and successfully sent to your server. The sources really stress that developers must verify this registration on every single app launch.
Every launch. Why?
Because device tokens can sometimes change, maybe after an OS update, or they can become invalidated for various reasons. If you're sending pushes to an old invalid token, they'll just vanish into the ether. So always re-register or verify on launch.
What about silent notifications? The ones where the app needs to wake up in the background to fetch new content or do some task without alerting the user immediately.
Silent notifications. Those are heavily regulated by the OS to save battery. For the system to even attempt to wake your app silently in the background, the notification payload must contain the specific key value pair content available. 1.
That exact key?
That exact key. You also need to have the remote notification background mode enabled in the app's Xcode capabilities section. And even then, be aware that if the user has force quit your app, the system generally won't deliver silent notifications. But getting the payload and capabilities right is step 1.
And if notifications are arriving, but they're significantly delayed, what could cause that?
That usually points back to one of two main things, either environment configuration or network reliability issues. You must verify your server-side API configuration. Are you accidentally sending production notifications to the Apple Sandbox APNS environment? Or vice versa. That mismatch will cause things to fail silently or be massively delayed.
Sandbox versus production. Got it.
The second possibility is just poor network connectivity on the device side. APNS tries its best, but notifications can often be delayed in areas with spotty Wi-Fi or cellular coverage because the device might prioritize user-initiated foreground traffic over lower priority background fetches like notifications. You need solid network reliability tests to rule out issues on your end versus just bad reception.
Okay, moving to background execution itself. The OS is constantly trying to terminate background tasks to save battery and memory. We know this. How do we ensure our potentially heavy lifting, like maybe syncing large data blocks or processing analytics, actually gets a chance to finish?
Yeah, you are constantly sort of battling the system's power management policies here. The first barrier to entry is enabling the appropriate background modes in your Xcode capabilities. You have to declare your intent, whether it's background fetch, remote notifications, location updates, audio, etc.
But those old modes have limitations, right?
They do. Especially the older background fetch APIs, they're pretty unreliable and severely time-limited by the OS. You might only get 30 seconds or less. For truly long-running, necessary tasks that need more time, they're often not sufficient.
So what's the modern approach?
For iOS 13 and later, the definitely recommended solution is the BG Task Scheduler framework.
BG Task Scheduler.
Right. This framework allows you to register and schedule specific background tasks with the system. You tell the system what kind of task it is, processing, network fetch, and roughly when you'd like it to run. The system then decides the optimal time to actually run it based on device conditions like battery level, network status, whether the phone is charging.
So the OS manages the timing?
The OS manages the execution window, making it far more reliable and battery efficient than the old background approaches where apps just tried to sneak in work whenever they could.
But what if the system still decides to terminate the task midway through? Say, the user starts playing a heavy game.
That can happen. And you must implement expiration handlers for your BG tasks. If the system decides it needs to terminate your background task before it's finished, your app gets notified immediately via this handler.
What should the handler do?
It needs to perform crucial cleanup actions very quickly. This means persisting any half-finished work, saving the current state, maybe canceling network requests gracefully so that the task can be safely resumed later when the system grants another execution window. Failure to handle expiration properly can lead to data corruption or just completely wasted background processing time.
Okay, makes sense. Now, for apps requiring constant location updates, which are notoriously battery draining, how do developers balance that need for continuous tracking with responsible power optimization? You don't want to kill the user's battery.
No, you definitely don't. You absolutely must enable the background location mode and capabilities. That's step 1. But the real optimization comes from tuning the level of detail you actually need.
How do you tune it?
You tune power usage by carefully setting the desired accuracy property and the distance filter property on the location manager. If your app only needs to know, say, when the user has moved roughly 100 meters, set a high distance filter. If you only need city-level accuracy, don't request GPS-level accuracy.
So don't ask for more precision than you need.
Exactly. Setting a higher distance filter or lower accuracy prevents the GPS chip and radios from waking up every single second, which dramatically reduces power consumption. This, in turn, reduces the risk of the OS terminating your app due to excessive power usage in the background. Be only as precise as necessary.
Finally, optimizing background network activity, especially uploads. If an app is uploading large videos or maybe doing a big data backup, how do we ensure that continues even if the user switches apps or locks their phone? Interrupting a big upload is painful.
Very painful. You absolutely must use URL session with a background session configuration. URL session configuration.background.
Why is that specific configuration so important?
It's essential because it delegates the actual responsibility of the network transfer, the uploading or downloading, to a separate daemon process run by the operating system itself.
Outside your app's process.
Exactly. This means the upload or download will continue transferring data even if your main app process gets suspended or even terminated by the OS due to memory pressure or inactivity. Your app just gets notified via delegate methods when the transfer eventually completes or if it fails.
That's pretty robust.
It is. Furthermore, when managing multiple simultaneous background uploads or downloads, you must limit the concurrency. You can't just kick off, say, 50 large uploads at once. That'll flood the network, likely lead to system throttling, and cause failures.
So manage the queue.
Yeah, experts typically use an operation queue with a specific max concurrent operation count, maybe limited to 3 or 4 concurrent network operations at a time, to manage resource usage efficiently. And always try to prioritize the mission-critical data uploads first, deferring less important or optional background tasks until the primary transfers are successfully confirmed.
Okay, our final pillar is operational excellence. The tooling and the pipeline that ensures stability remains high even as you push out hundreds of releases. Why is automating the CI/CD process, continuous integration, continuous delivery so crucial for mobile development specifically?
Oh, automation is absolutely key because the manual process of building, code signing, archiving, and uploading apps via tools like TestFlight or the App Store Connect website is notoriously time-consuming, incredibly repetitive, and frankly, extremely error-prone.
Especially the code signing part.
Certificates, provisioning profiles, it's a minefield. The goal of automation using CI/CD is really twofold. First, it ensures every build is consistent and reproducible. Second, it provides continuous rapid feedback to the QA team and stakeholders.
Faster feedback loops.
Much faster. This radically accelerates the delivery cycle from code commit to testable build, and it minimizes those painful configuration mistakes that can often lead to weird production-only crashes that never showed up during development.
What are the primary workhorse tools that typically stitch together this automated pipeline for mobile?
The pipeline usually relies on 2 main layers. The automation scripting layer often uses Fastlane. It's fantastic for scripting complex mobile-specific tasks like automating code signing, running unit and UI tests, managing build numbers, and handling uploads to TestFlight, or even generating release notes.
So Fastlane handles the mobile-specific steps. What does the compilation?
Below Fastlane, the fundamental compilation, archiving, and exporting work is handled by the Xcode command line interface. CLI tools, specifically the Xcode build command.
Okay.
This Xcode build command is typically triggered by a more general CI/CD platform like GitHub Actions, Jenkins, GitLab CI, or Circle CI, which usually run on dedicated build machines or cloud runners. So the CI platform orchestrates, Xcode build compiles, and Fastlane automates the mobile deployment details.
Before we leave automation, let's quickly revisit the core crash reporting tools you mentioned earlier. We heard Crashlytics, Sentry, Bugsnag, Instabug. They all seem to do roughly the same thing at first glance. Can you clarify their differences in focus? How does a team choose?
Yeah, they overlap, but they definitely have distinct specializations and strengths. Crashlytics, which is part of Firebase and Google, is very tightly integrated with the Google ecosystem. Its primary focus has traditionally been on robust crash reporting, specifically for mobile operating systems, iOS and Android. It's often praised for its quick setup and deep insights into stability issues.
Okay, Crashlytics, mobile crash focus. What about Sentry?
Sentry has a broader focus. Yes, it does error monitoring and crash reporting, but it supports a huge range of platforms beyond just mobile web front ends, back ends, etc. It also puts a strong emphasis on performance monitoring, tracking things like transaction speeds and identifying performance bottlenecks, not just crashes.
So Sentry is broader, more performance-oriented. Bugsnag.
Bugsnag also emphasizes stability monitoring, similar to Crashlytics, but it differentiates itself with features focused heavily on stability scoring and automatic prioritization. It tries to help teams understand the real user impact of crashes and triage which ones to fix first based on calculated stability scores.
Interesting. And Instabug.
Finally, Instabug takes a different angle. It combines crash reporting with a suite of tools focused on in-app user feedback. Think bug reporting directly from within the app, user surveys, session replay features. It's heavily focused on the user experience, UX side of things, and is often very useful for beta testing phases or gathering feedback directly from non-technical stakeholders and end users alongside the crash data.
That clarity definitely helps teams choose the right tool, or maybe even combination of tools, for their needs. Now, let's talk about the absolute nightmare scenario. The app works perfectly fine in debug mode on your machine, but it crashes only in production builds distributed through TestFlight or the App Store. What causes this, and how on earth do you debug a crash you literally cannot reproduce locally?
Yeah. That's one of the toughest situations a mobile developer faces. It is almost always caused by differences in the build configuration between debug and release modes.
Like what specifically?
Specifically, release builds often employ aggressive compiler optimizations. For example, using the O-size or O-speed optimization flags, which prioritize minimizing the app's binary size or maximizing execution speed. These optimizations can sometimes subtly rearrange code execution, change timing, or even inline functions in ways that expose delicate race conditions or sensitive memory management issues that simply never surfaced in the slower, unoptimized debug builds.
So the optimization itself causes the bug to appear?
It doesn't cause the bug, but it can expose a latent bug that was always there, but hidden by the less aggressive debug environment.
So the strategy moves away from trying to break point locally and towards getting maximum visibility into what happened in that production crash environment, right?
Exactly. You first have to meticulously verify any build configuration differences between debug and release. But the most critical step by far is ensuring you have proper symbolication set up for your production crashes.
Symbolication, what does that mean?
It involves uploading your DSYMs, which stands for debug symbols files, to your chosen crash reporting tool, like Crashlytics, Sentry, etc. A raw production crash stack trace is just a series of cryptic memory addresses. It's completely unreadable.
Just numbers.
Just numbers. Without the corresponding DSYM file for that specific build, those addresses are meaningless. Uploading the DSYMs allows the crash reporting tool to translate or symbolicate those addresses back into human-readable function names, file names, and even line numbers from your original source code.
So you can actually see where in your code the crash occurred.
Precisely.
Yeah.
It lets you instantly see where the crash happened in your actual source code, which is the essential first step to understanding and fixing it. Without DSYMs, you're flying blind on production crashes.
A related headache, and our last point here, is integrating third-party SDKs. They add functionality quickly, but sometimes they introduce instability, bloat the app, or maybe even violate hidden App Store rules. How do we investigate a flaky or suspicious third-party dependency?
Yeah, third-party SDKs are a double-edged sword. The investigation needs to be systematic. First, obvious but critical. Read the SDK documentation thoroughly. Check their integration steps, any required dependencies they have, supported OS versions, known issues.
RTFM.
Basically, pretty much. Second, you must isolate the SDK usage. If you suspect an SDK is causing instability, create a minimal proof of concept project. A tiny test app where that SDK is the only external dependency. Try to reproduce the instability there away from the complexity of your main application's codebase.
Makes sense. Isolate the variable.
Exactly. Third, and this is really crucial for App Store compliance, consider using static analysis tools or just carefully inspecting the SDK's headers or code if possible. You need to check for the use of any deprecated Apple frameworks or worse, private APIs that might conflict with Apple's App Store review guidelines. An SDK could get your app rejected.
Good point.
And finally, always verify the dependency versions carefully. You'd be surprised how often a crash is caused by two different third-party libraries in your app demanding incompatible versions of a shared underlying dependency, maybe like Alamofire or something. This can lead to weird symbol conflicts or unexpected behavior at runtime. Managing dependencies carefully is key. #outro. Wow. Okay. We have covered a massive amount of technical ground in this deep dive, haven't we?
We really have.
The journey moved pretty seamlessly, I think, from stabilizing those volatile UI elements like table views and eliminating silent memory leaks using precise tools like instruments.
Right, like the memory graph debugger in Zombies.
Exactly. All the way through to ensuring complex asynchronous network calls resolve gracefully and making sure critical background tasks actually finish reliably using newer frameworks like BG Task Scheduler.
The common thread weaving through all 5 of these pillars, as you really emphasize throughout, seems to be that core principle of aggressively moving heavy processing off the main UI thread.
Absolutely.
Embracing asynchronous methods wherever possible, and then leveraging precise debugging tools and solid automation in the pipeline to maintain visibility and control across the entire development lifecycle.
And what's really fascinating here, looking back at all these Q&As, is that the solutions aren't just, one-off technical fixes for isolated problems. They represent systemic, repeating architectural patterns that truly define high-quality mobile software.
Patterns like
We see the consistent application of using weak self-enclosures to prevent retain cycles and ensure stability. We see using tools like debounce or throttling combine for flood control on rapidly updating UI. We see relying on asynchronous fetching and batching for responsive data presentation from core data or network calls. These systemic choices applied consistently are the defining differences between an app that just kind of works acceptably and an app that truly excels under real-world pressure and constraints.
It's honestly incredible how much rigorous attention to detail goes into preventing something that seems as simple to the user as maybe a flickering view during a data update or a notification that shows up a few seconds late.
Right.
It makes you realize just how fragile the mobile ecosystem can be under the hood, and how absolutely essential this kind of architectural rigor and discipline development really is.
Indeed. And, we saw the importance of reliable background execution and the limits the OS imposes there. But this naturally leads us to maybe a final provocative thought for the listener to chew on. Since the OS is only getting stricter about power consumption and constantly reducing those precious few seconds it grants to apps for traditional background fetch, how might future app architectures need to shift even further to guarantee real-time reliability?
Meaning move away from background fetch entirely.
Perhaps. We saw a brief mention in the sources about potentially using more event-driven update mechanisms like persistent WebSockets instead of relying on polling or periodic background fetches. Maybe the ultimate frontier for reliability in the face of these OS restrictions is moving entirely towards persistent, real-time communication protocols. That way, you could potentially avoid relying on the OS's unpredictable background scheduling limitations altogether for critical updates.
Interesting. A shift from pull to push, essentially managed by the app's connection.
Something like that. Definitely something for you to mull over until our next deep dive.